deposits. Eventually, we're going to see that heat spill into the Colorado Rockies, and that's going to prompt further snowmelt from a season that wasn't beneficial for everyone.
Water and land use in the American West are some of the biggest issues.
The first signs of trouble appeared long before anyone realized what they meant. High-resolution interferometric satellite scans passing over the Colorado River Basin registered a faint but unmistakable deformation in the crust, a subtle warping that stretched across a broad corridor beneath the river's winding path. The initial data looked like noise, the kind of atmospheric distortion analysts regularly filtered out. Yet, as successive satellite passes refined the image, the anomaly sharpened into something that could no longer be dismissed: a measurable seismic shift running parallel to one of the most geologically complex river systems in the western United States. Before we start, smash the like and subscribe buttons for more updates. This development, once verified by ground-based instrumentation, propelled the United States Geological Survey into issuing a rare internal red alert designation for heightened seismic risk conditions. The alert marked the moment when a pattern of unassuming tectonic tremors revealed itself to be part of a larger, coordinated movement deep underground. Though the continental interior is not typically associated with rapid tectonic reconfiguration, the pressure in the region had been accumulating for decades, masked by the slow-motion nature of intraplate stress changes. The new satellite data simply lit up what had already been brewing unseen beneath the surface. The Colorado River Basin is not a monolithic formation. It is a complex patchwork of faults, eroded plateaus, sediment layers, volcanic remnants, and ancient structural weaknesses. While the region is not considered dormant in a geological sense, it has seldom attracted the kind of alarm reserved for major fault lines along plate boundaries. That changed the moment scientists realized that the newly detected deformation was not isolated. Instead, it appeared interconnected across multiple subsurface zones, creating a network of strain pathways that hinted at an evolving seismic episode. The red alert designation was not an announcement to the public, but a classification used by experts to indicate a potentially developing situation that demanded immediate, intensive scrutiny. The satellite readings showed a displacement pattern consistent with deep crustal flexure, a bending caused not by a single slip, but by a series of interacting shifts. This type of deformation can sometimes precede more noticeable seismic behavior, yet it can also persist quietly for years without escalating. The challenge lay in determining which direction this situation might lean. The basin's long-ranging geological history is full of episodes where forces strain silently beneath layers of sandstone and shale before revealing their presence in a sudden rearrangement of the landscape. Modern technology now offered the clearest lens ever produced to observe such processes in near real time. As experts studied the satellite-derived measurements, they saw something more unsettling than the deformation itself. The movement suggested a reactivation of segments of ancient faults that had not produced notable seismic events in recorded history. These faults, buried beneath millions of years of sediment deposition and erosion, often behave unpredictably. Their internal structure can be more irregular than faults in actively shifting regions, with locked sections that may resist movement until the surrounding crust redistributes pressure enough to force them into motion. The implications of such reactivation were difficult to quantify but impossible to ignore. One of the most significant concerns stem from the role the Colorado River plays in carving and maintaining the landscape across vast swaths of the American West. The river's path is intertwined with the region's geology in nearly every conceivable way. Its flow, elevation profile, canyon depth, and sediment load depend heavily on the stability of the crust it traverses. A seismic shift beneath this environment raised questions about potential changes in slope gradients, channel dynamics, and groundwater movement. While none of these possibilities guaranteed immediate disruption, the interconnected nature of the basin meant that any alteration in subsurface structure could eventually influence the system above it. The USGS team assigned to the situation began reconstructing the sequence of events leading to the detected deformation. Their models revealed a series of micro-slip episodes progressing through the deeper sections of the crust. creating a chain reaction that satellite imagery captured as surface displacement. Though imperceptible to anyone living above, this motion signaled a process unfolding tens of kilometers underground. The crust in this region can behave in complex ways, transitioning from brittle near the surface to ductile at greater depths. This blend of rigidity and plasticity can cause strain to accumulate in unusual patterns, often leaving geologists uncertain about where or when stress will be released. The red alert status for seismic research meant that monitoring stations across the basin were placed into priority mode. Instruments began collecting data at higher sampling rates to capture any fluctuations in background seismic noise. Even the most minor signals were scrutinized, from tiny harmonic tremors that could indicate fluid movement to low-frequency waves that might point toward deeper tectonic adjustments. These observations were crucial to understanding whether the shift represented a temporary fluctuation or the early stages of a more sustained change. One unexpected implication of the seismic shift involved the region's intricate network of aquifers. Much of the water movement beneath the Colorado River Basin occurs through porous rock pathways that can be altered by tectonic stress. When faults slip or when the crust flexes, these subterranean corridors can narrow, widen, or realign. In some cases, this can divert water flow in new directions or create pressure pockets that influence springs, seepage zones, and even the stability of slopes along canyon walls. While none of these effects were guaranteed, they became critical lines of inquiry as the implications of the shift continued to unfold. Another dimension of concern revolved around the broader tectonic setting of the southwestern United States. The basin sits in a transitional zone between the extensional forces of the basin and Range Province and the more stable interior of the continent. Though not as dramatically stretched as Nevada or Utah, parts of the Colorado Plateau have experienced slow extension over millions of years. The newly detected movement hinted that this slow deformation may be undergoing a temporary acceleration, possibly triggered by long-term changes in crustal loading, mantle convection dynamics, or stress redistribution from distant seismic events. Understanding which of these forces played a role would be essential for predicting future changes. If the shift represented a deeper reorganization of stress within the crust, the implications could extend beyond the immediate region. Stress changes can propagate across large distances in subtle ways, influencing the behavior of nearby fault networks. Even faults considered relatively inactive might experience slight adjustments due to shifting pressures. While this does not necessarily translate into increased seismic hazard, it underscores the interconnected nature of geological systems. A shift detected in one location can be part of a broader regional response occurring on timescales far longer than human observation. The satellite technology responsible for detecting the deformation relied on interferometric processing, where successive radar scans reveal minute changes in surface elevation. This method has revolutionized the study of seismic precursors, allowing scientists to observe crustal movement with millimeter precision. In this scenario, the technique exposed patterns that would have remained invisible only a decade earlier. Such data sets a new frontier in understanding the subtle first stages of seismic development, particularly in areas not traditionally monitored as potential hotspots. The possibility that the tectonic shift could influence surface morphology raised further questions about long-term landscape evolution. The Colorado River has been a persistent sculptor of the terrain for millions of years, cutting canyons, distributing sediment, and shaping valleys. A change in the underlying tectonic regime, however slight, could gradually shift this equilibrium. Even small alterations in uplift rates can change erosion patterns, accelerating canyon carving in some areas while slowing it in others. Over long spans of time, the result could be a noticeable redefinition of the plateau's topography. Geophysicists studying the event paid close attention to the relationship between the movement and deep-seated magmatic systems. While the region is not dominated by current volcanism, remnants of ancient volcanic fields lie scattered across the basin. These old systems still contain cooled magma bodies at depth that can subtly influence the mechanical properties of the crust. If the detected shift occurred near one of these zones, it might reflect changes in how stress interacts with stiffer or weaker rock structures. This consideration broadened the investigation, incorporating petrological data and crustal imaging to create a comprehensive picture of what lay beneath the surface. Beyond the immediate scientific scrutiny, the implications also touched on long-term geological forecasting. Seismic shifts in regions like the Colorado River Basin challenge established assumptions about which areas are considered more or less tectonically active. The discovery of unexpected crustal movement forces geologists to revisit models and reassess zones where ancient faults lie buried beneath layers of sediment. Over time, as more satellite data becomes available and more subsurface mapping is completed, these models evolve into increasingly accurate representations of the forces shaping the land. Earth scientists recognize that the crust does not shift without reason. Every movement, no matter how minute, is part of a larger system governed by the balance of forces within the planet. These forces include gravitational loading, mantle flow, thermal contraction, and even the long-term rebound from ancient glaciations. Determining which element is responsible for the current shift requires extensive analysis, yet each possibility carries implications for understanding the future stability of the region. For example, mantle flow variations beneath the basin could signal a deeper, slower process unfolding beneath the western United States, one that subtly but steadily rearranges stress fields. The detection of the seismic shift also drew attention to the importance of continuous monitoring. While dramatic earthquakes capture public attention, the vast majority of tectonic evolution occurs quietly. Such silent shifts occurring at depths unreachable by drilling or direct observation offer crucial clues to the behavior of continental interiors. The Colorado River Basin situation highlighted how essential satellite observation has become in revealing these hidden dynamics, acting as an extension of ground instrumentation and providing data from angles once unimaginable. One of the more intriguing scientific implications involved the potential relationship between the shift and regional geothermal gradients. Certain areas within the basin exhibit higher than average heat flow from the mantle, a remnant of past volcanic activity and crustal thinning. Elevated heat flow can weaken rock at depth, making it more susceptible to deformation. If the newly detected movement aligned with zones of higher geothermal activity, it could suggest that these weakened areas were facilitating the transfer of stress between deeper and shallower layers of the crust. This possibility required integrating geothermal data with seismic readings and satellite imagery, creating a multidisciplinary approach to understanding the event. While the satellite data captured surface deformation, the interpretation of this information relied heavily on advanced numerical modeling. Researchers developed simulations that tested various scenarios: changes in stress due to crustal flexure, reactivation of buried faults, elastic rebound from previous seismic cycles, and even the gradual impact of erosion removing mass from the plateau. These models offered a window into the likely mechanics behind the shift, refining hypotheses through iterative adjustments based on real-world measurements. The geology of the region is shaped by eons of uplift, erosion, and tectonic reconfiguration. The Colorado Plateau, though considered relatively stable, sits within a broader context of dynamic crustal behavior. The uplift that elevated the plateau began millions of years ago, possibly triggered by mantle buoyancy changes or lithospheric thinning. The new seismic shift raised the possibility that adjustments to this uplift process were still ongoing in subtle ways. Even slight changes in uplift rate can influence the tilt of the land, potentially altering river gradients over vast distances. As researchers continued examining the implications, they also considered the long-term interactions between tectonics and hydrology. The Colorado River's path is influenced not only by the bedrock it cuts through, but also by the tectonic forces that guide the slope of the terrain. A shift in the crust could lead to changes in the river's equilibrium profile, perhaps altering the rate at which sediment is transported downstream. Over long time periods, such changes can influence delta formation, channel migration, and the distribution of sediments across tributaries. Another layer of complexity arose from the presence of salt beds beneath parts of the basin. These evaporate layers can deform plastically under pressure, causing subsidence or uplift depending on stress conditions. If the seismic shift induced changes in pressure on these salt beds, the resulting deformation could propagate upward, affecting surface structures and altering groundwater movement. Though speculative, this interplay between tectonics and evaporate mechanics was worth exploring, given the unusual geological architecture of the basin. As analysis deepened, attention turned to the possibility that the seismic shift reflected a transfer of stress from one structural block to another. The crust beneath the basin is segmented into distinct blocks separated by fault zones. These blocks can behave independently, each responding differently to tectonic forces. If one block begins to shift, it can push or pull on its neighbors, creating a cascade of subtle adjustments. Understanding these block interactions is essential for constructing accurate models of intraplate seismicity. Scientists also explored how deep-rooted lithospheric processes might contribute to the observed deformation. The lithosphere beneath the western United States has experienced complex modifications due to past subduction, mantle upwelling, and regional extension. If mantle flow patterns shifted even slightly, the stress distribution within the overlying lithosphere could change accordingly. This kind of coupling between deep earth processes and surface expressions often occurs on timescales far beyond human perception, but becomes visible through the precision of modern satellite imaging. In considering the broader implications, researchers noted that the basin's geological behavior cannot be studied in isolation. It interacts with adjacent regions, undergoing extension, uplift, and fault activity. By placing the seismic shift within a regional framework, scientists gained a clearer understanding of how the Colorado Plateau participates in the tectonic evolution of the western United States. This perspective helps refine long-term models of crustal stability and offers insights into how tectonic forces propagate through continental interiors. Overall, the detection of the seismic shift represented an opportunity to deepen knowledge of an intricate, evolving landscape. The Colorado River Basin, with its layered geological history, its complex web of hidden faults, and its dynamic relationship with the forces shaping the crust, became the focal point of an investigation into how subtle movements can reveal the slow rearrangement of the Earth beneath our feet. The implications stretched far beyond the initial satellite detection, inviting continued exploration into the structural, hydrological, and tectonic processes that define this remarkable region. The renewed focus on the basin's shifting dynamics also opened a pathway for examining how sediment compaction contributes to long-term crustal behavior. Although often overshadowed by tectonic processes, the gradual compression of ancient river deposits and marine sediments can subtly influence how stress moves through the region. As these layers compact under their own weight and the overlying rock, they can create zones of differential rigidity that redirect seismic energy or concentrate strain in unexpected places. The newly detected deformation brought fresh attention to these quieter, slower processes that often interact with tectonic forces in ways not fully understood. Another aspect gaining attention involved the interplay between deep-rooted fractures and the chemical composition of circulating groundwater. Over geological timescales, water percolating through fractures can dissolve minerals, enlarge pathways, and weaken structural boundaries. If the seismic shift altered the configuration of these underground networks, even slightly, it could accelerate or redirect the chemical alteration of the rock. Though this kind of change unfolds gradually, it influences future mechanical behavior by modifying the elasticity and strength of certain formations. These changes, while invisible on the surface, become crucial components of long-term tectonic evolution. Researchers also turn their attention to the mineralogical transitions occurring at depth, where pressure and temperature conditions differ dramatically from those near the surface. In these zones, minerals can undergo transformations that alter their density and mechanical properties. Such transformations can either absorb or release stress depending on the type of mineral involved. If the seismic shift intersected with regions undergoing active mineral phase changes, it could imply a deeper thermodynamic influence contributing to the event. Understanding these transitions required integrating seismic tomography, laboratory simulations, and pressure temperature modeling to capture a full picture of what might be unfolding miles beneath the river system. Attention also shifted toward the timing of the seismic shift in relation to long-term climate cycles. Changes in precipitation patterns, snowpack weight, and river discharge influence the load distribution across the basin. Though subtle, these changes can modulate the stresses acting on the crust, especially in regions where elevation and erosion are tightly linked to climate. If the deformation aligned with shifts in hydrological load, it might reveal a link between surface climate variability and deeper tectonic processes, emphasizing how complex and interconnected the Earth system truly is. In addition, the role of ancient tectonic sutures, deep scars left behind by long-vanished continental collisions, became a significant point of inquiry. These sutures often contain weakened rock zones that can reactivate under renewed stress, even if the original tectonic event occurred hundreds of millions of years ago. If the seismic shift involved the subtle movement of one such suture, it would provide rare insight into the lingering influence of prehistoric continental assembly on present-day geological behavior. Each of these developing lines of inquiry extended the significance of the shift far beyond the initial satellite detection, turning a momentary anomaly into a catalyst for deeper exploration of the forces shaping one of the most complex and storied landscapes on the continent. If you like this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us, what are your thoughts on this Colorado River seismic shift and red alert prediction? We want to hear from you. Thank you for watching and see you next time.